Welcome, ladies and gentlemen, to this video lecture. Let's take a look at this theorem. So let's say we've got functions f and g, and we've got numbers a and b in the reals. If f is continuous at b and the limit of g of x as x tends to a is equal to b, then what we have is that the limit as x tends to a of the composition of f and g, so f applied to g applied to x, is then equal to f evaluated at b. So here we have this word continuous. Let us reiterate what the definition of continuity is. So definition, continuity. So f, defined on the reals, is continuous at a if the limit as x tends to a of f of x is equal to f of a. So we say f is continuous at a if the limit as x tends to a of f of x is actually equal to the function value at a. So here we have our definition. Okay, so let us prove this theorem. So again, as always, you start with your proof outline. Proof outline. So we want to prove this implication. So we assume that f is continuous at b. So f is continuous at b. Let's write it this way. So we assume 1, f is continuous at b, and assume 2, the limit as x tends to a of g of x is equal to b. So here are our assumptions. Maybe let's change the layout a little bit. I don't like it. Like so. So here are our two assumptions. And what we want to conclude is that the limit as x tends to a of f applied to g of x is equal to f of b. So perhaps pause the video and write down the rest of the outline and see how it compares with what I write down. Okay, we want to conclude this in the end, but this means something very specific. It means for every epsilon. So we go and we say we fix any epsilon greater than 0. We must define a delta somehow, and this delta must be positive. If, so we assume 0 is less than x minus a, less than delta, then we want to conclude that f of g of x minus f of b is less than epsilon. That is what we finally want to conclude. So here is our proof outline. Okay, let's fill in the details. Okay, so we need to construct this delta over here. And how can we construct this delta? We have to somehow use these assumptions. So these shops that we have, that we can buy deltas at. Okay, let us I'm going to duplicate these two pages. So duplicate that page and let's move it. Can we move it? Yes. And I want to duplicate this page and move it to the end. Here we go. Okay. Before we fill out the details, let us think about how we will go about it. So I need another page. Page after. Okay. This proof happens in 3 layers. So what do we have? So I'm going to put 3 copies of the real line here. And we've got here we've got f going from R to R, and here we've got g going from R to R. And we want to show something about the limit as x tends to a of f applied to g. So here we've got an a, and here we've got the value of the limit of that is b, because the limit as x tends to a of g of x is assumed to be equal to b, and b f is assumed to be continuous at b, meaning that the limit as x tends to b of f of x is equal to f of b. That is because f is continuous at b. Okay. So now what we will do is, as we've done here, we fix any epsilon. So we take any epsilon interval around f of b. Since f is continuous, we can use the assumption that it is continuous to find a delta 1 around b, so that everything in this interval, in this delta 1 interval around b, maps into this epsilon interval around f of b. But we know something. Why don't we use this delta 1 as the epsilon in the definition of g to construct a delta 2, so that the delta 2 interval around a is such that everything in this interval maps into this delta 1 interval. And if you chain it all together, everything in this interval maps in here, but everything in here maps in to that interval. So that is what we will do. Okay. And you see now why I say this proof happens in layers. And it might be useful to not think about things in a Cartesian plane, but to have but to think about it in this way of copies of the real line mapping into other copies of the real line. Okay, so let us put this idea into practice. So let's move this down a little bit. So this epsilon, so fix any epsilon, we will use this epsilon with f to get a delta. So by 1, there exists a delta 1 greater than 0, so that if 0 x less than b is less than delta 1, then f of x minus f of b is less than epsilon. And I need more space, so I will move this down. Cut, paste. There we go. Okay. But now, what we will do is, let's set epsilon 1 to actually be equal to delta 1. And now we will go by another delta, but now from 2 with this epsilon. So by 2, there exists a delta 2 greater than 0, so that if 0 is less than x minus a is less than delta 2, then g of x minus b is less than epsilon 1, but epsilon 1 we define to be delta 1. Okay, and now the delta that we're looking for is, of course, the delta that we have here. So this is this will be delta 2. So we define delta to be delta 2, and let's see what happens. So we assume that that is true, but delta is equal to delta 2. Then what do we have? We've got g of x minus b is less than epsilon 1, which is less than delta 1. Okay, but we know, so but if x minus b is less than epsilon 1, then f of x, well, actually let's use a different symbol just to emphasize. So if y of minus b is less than epsilon 1, then f of y minus f of b is less than epsilon. And epsilon 1 is the same as delta 1. So what have we got? But we have this. So if x minus a in absolute value is less than delta, g of x minus b is less than delta 1. So, but for any y for which this holds, we've got that. So g satisfies this condition. Therefore, we've got f of, or let's write here, so but if x minus a greater than 0, less than delta, then g of x minus b is less than delta 1. But then
adding Sprinkleback capsule. Please unlock your device for this.
But then we've got f of g of x minus f of b is less than epsilon. And they were done. So let's go through this again. Let's start with our diagram here. We know that f is continuous at b over here. That means for any epsilon, there exists a delta 1, so that if we look at the delta 1 interval around b, everything in that interval maps into this epsilon interval around f of b. But now we use this delta 1 as the epsilon in G to construct a delta 2, so that everything in this delta 2 interval maps into this delta 1 interval around B. And then we put everything together and we see everything in here, if we compose F with G, then everything in here, the composition of F with G maps everything in this interval into that interval. So let's go through our proof again. And this is now our proof for realsies. We assume that F is continuous at B, and we assume that the limit as x tends to A of G of x is equal to B. We fix any epsilon. We construct our delta so that if x is close to b, within a delta 1 distance of b, then f of x is within an epsilon distance of f of b. Then we take this delta that we have just constructed, or that we have just bought from shop 1, and we use it as our epsilon, and we go buy another delta, different delta, from shop 2. So we use this delta as the epsilon. We set epsilon 1 equal to delta 1. By 2, there exists a delta, so that if x minus a is less than delta 2, then g of x minus b is less than epsilon 1.
I'll need a formula to calculate.
But epsilon 1 is defined to be delta 1.
Try telling me a different formula, or saying the formula.
Okay. Then what are we looking for? We are looking to define a delta. We just take our delta 2 here, and this is what we've done here on our diagram. So we've first find our delta 1 here at this level. We use that as our epsilon to find our delta 2 at this level, and on this level we just define delta to be our delta 2. And now we should show that if this holds, then f of g of x is within an epsilon distance of f of b. So we assume that this holds, but by how we've defined our delta as delta 2, we obtain exactly this, that g of x minus b is less than epsilon 1, which is not in fact less than delta 1, it is in fact equal to delta 1. That is how we have defined epsilon 1. But by definition of delta 1, if y minus b is less than delta 1, f of y minus f of b in absolute value is less than epsilon. But if this holds true, g of x minus b in absolute value is less than delta 1. So if you take this g and you substitute it into f, you get exactly what you want. Because if this holds true, this holds automatically true, so we can replace this y by g of x, because this g of x satisfies the condition that we're looking for. G of x minus b is less than delta 1, but if anything minus b is less than delta 1, we've got f of that anything minus f of b is less than epsilon. And that is what we obtain here. And that completes this proof. I will see you in the next one.